Okay, so Pre-Calculus 20, Unit 3 starts with Chapter 5, and Unit 3 talks about functions and equations. So we're going to study different types of functions, different types of equations, what the solutions to these equations mean, what the different types of functions might represent. And so in the real world, if you're doing any kind of calculation, or if the machines that you're working with are doing calculations, they are working with functions. They're working with basically descriptions of how variables are related to each other. So you see that in all sorts of, this looks like radar, all sorts of satellite communications, meteorology, predicting storms. There's models, there's functions of weather models that are mathematically based, that are generated all the time, and they're able to help people predict weather and stuff like that. So you've had a chance to read through that a little bit. Chapter 5 is about radical expressions and equations, and you've had some experience with that last chapter with the quadratic formula, right? X equals negative b plus or minus root b squared minus 4ac all over 2a. That root is a radical, okay? So the root sign is called a radical. And there are other radicals. There are cubed roots and fourth roots and fifth roots and seventh roots and 11th roots and all that sort of stuff. Anything that has that little root sign, whether it's a square root or another kind of root, is referred to as a radical. Okay? So we're going to talk about that a little bit this chapter. And again, there's a lot of interesting things to look at and explore in your textbook. Okay, so 5.1. So the basic lesson 5.1 is working with radicals. And again, you've had some experience, and I've gone over this a little bit already before, but we're going to go over it a little bit more in depth today. And I believe that you've had experience with this in previous math classes. But we're going to talk about simplifying radicals, adding and subtracting, multiplying radicals, and all that sort of stuff. We're going to get comfortable today with working with radicals of all sorts of and kinds. So I want to just kind of skip to this part of the lesson. Like radicals, okay? So if you want to join me on that page, what page is that again? That is page 273. Like radicals. Okay, so I've got this clipped into the notes here just so I can kind of draw on it a bit. Like radicals and unlike radicals. Whoops. So the radical part of a number would be like this part here, the root 7 part. 5 root 7 would be literally a group of 5 root 7s. Okay, so if you add root 7 5 times, that's the same as 5 root 7. 5 times root 7, or 5 root 7s added up. Okay, same thing. So if you look at this, a like radical would be a radical that has the exact same business underneath the root sign there. Same numbers, same variables, same exponents on all of those. Those would be like. So notice that these are all alike, so we are able to add them up. Just like apples are alike with other apples. So if I have 2 of the same apples, you don't say I have 1 apple and 1 apple. You say I have 2 apples. If I had an apple and a banana, those would be unlike terms. So you couldn't say I have 2 apanas. No. You say you have 1 apple. It's funny. 1 apple, it's English. 1 apple and 1 banana. Okay? I don't even know what I said there. 2 apanas. Apapananas. I don't know. But you know what I mean? So those are unlike. You can't group them into one term. So hopefully that should maybe help. I don't know. Apananas? So if anyone is able to cross an apple with a banana and bring that fruit to me, I will congratulate you. A banana. Mr. MathWell, a banana. Okay. Unlike radicals. Okay, notice. Watch this. Everyone listening? This is like, and I'll just zoom in so you can see this, 2 root 5 and 2 root 3. So all of this stuff underneath the radical, these are different. And even with different types of radicals, those are different. We have the same stuff underneath here, but if the type of radical is different, these are unlike. So it has to have the same stuff underneath the root sign, and the radical has to be the same type of radical. Notice these are both cube roots. Now this little number that's in here, this 3 in this case, and the 4 and the 5 in these cases, that's called the index of the radical, the index of the root, or the index of the radical, index. And that literally means we're going to take the 4th root of the number. So it's asking for, if you're able to calculate, so for example here, let me talk about that real briefly. If we had the, let's say, the third root of 8. I'm looking for what number multiplies by itself, so what number to the power of 3 equals 8. That's what I'm actually looking for. That's what this equals. So this index means what number cubed gives me 8. And of course that's 2, right? So if we had the fourth root of 16, I'm looking for what number times itself 4 times gives us 16. That's 2 as well, right? So that's what the index means, unlike like. Okay. We can add like radicals. We cannot combine and add unlike. We can always add anything, but we can't lump it into one term. That's what I mean. Okay. So another example here, if you had, I'll change colors. So if I had 3 root 3 plus 2 root 3 plus 7 root 2, I could add these two terms because they are like terms, and I have 3 and 2, so I have 5 root 3's there. But I can't lump this into this one term as well. I have to write it separately, and that's your final simplified answer, okay? Unlike terms, you can't combine into one term. Okay, moving along. Restrictions on variables. So when we're talking about radical equations, we have to look at what values for the variable, in this case x, are not allowed. Now there are some values that aren't allowed. For example, if you're measuring, and we're going to talk about that in MathLab a little bit later. Okay, we're going to do that towards the end. If you're talking about a distance from start, like just a straight old distance, how far can you walk in 2 minutes or whatever, the answer wouldn't be negative. Even though you can walk backwards, that's a different situation. Okay, the positive and negative, if that's displacement, if it's direction involved, then yeah, negative's okay. But if we're talking about the length of the side of a square or something, you can't have a negative length of a side of a square. What does that look like? It doesn't exist. It doesn't make sense. Or if you're timing yourself, how long does it take you to run up the stairs? And if you say, well, it took me negative 5 seconds. Really? So you were up there 5 seconds before you started running? Oh, that's interesting. Not possible. So there are some restrictions, right, on our solutions and our variables. So restrictions on the variable. Look at this, a square root. You cannot take the square root of a what number? What type of number? It cannot be what underneath here? Anybody? Negative. You cannot take the square root of a negative number. Okay? Doesn't work. What number times itself gives you a negative number? Nothing. If you have a negative number times itself, another negative, 2 negatives equal a positive. If you have 2 positive numbers, multiply those together, that equals as well a positive. So when you go backwards and take the square root of a number, you'll never get a negative. So you can't take the square root of a negative number. Well, actually I said that wrong. You can take the square root of a number and the answer could be negative, but you can't take the square root of an already negative number. It doesn't work. So restrictions, if you have something like this, what are the non-permissible values of x? Well, if this was to be negative, what x value would make this negative? Or in the positive sense, this has to be greater than or equal to 0. And so what values for x are allowed? In this case, when we solve for x, we see that x has to be less than or equal to 4. Has to be less than or equal to 4 in order to make this positive. So that means that x cannot be greater than 4. If x was greater than 4, then this would be a negative under here. Everyone see that? So that's a little bit of work with domain, but just remember this, that underneath the square root, or really any root that has an even number, so square root or fourth root or 6 or 8 or 10 or 12, you cannot have a negative number under there. Okay? The odd indexes you actually can, but we might get into that a little bit later. All right, the next big thing here is knowing how to convert. You should have some experience with this, but let me just go over this because this may be, you may need a refresher on this. Okay? So, all right, so example 1. Now, you can write these down, please, in your notes, just so you can see this worked out. I know it's in your textbook, but you need to work this out and kind of feel it yourself. So express each mixed radical in entire radical form. Okay, well, let's go back here. Mixed radical. A mixed radical is where we have a rational part and an irrational part, or we have a number that's outside of the radical and a number that's, or a term that's inside the radical. So this is mixed. It's got both parts. All right? So how do I make the mixed radical an entire radical? Well, an entire radical is where everything is entirely underneath the radical. Everything is inside the radical. Now, the way I've taught this before is I say, okay, this 7 is not inside the root here, right? It wants to get into the square root club. This is the club in there. And it's hopping in there. That 2 is having quite the time, okay? There is a party going on inside the root club. Now, the 7 wants to get in there. But, you know what? Unfortunately, the 7 just can't jump in there as a 7. Can't do it. If you want to get into the square root club, you got to get squared. Okay? If you want to get into the root club, you want to get squared. So this 7 can come in, but it's got to go in as a 7 squared. And so this is actually then 2, and you multiply everything that comes in. 2 times 49, and that's going to be, what's that, 96, 98, 98. Okay? So the square root of 98 is actually the entire radical. That's the same as 7 root 2. All right? So this a to the 4th, now you have to be very careful. This 4 is not inside the root here. It's not an index. It's on the a. This is a to the 4th, and this is a square root. So a to the 4th wants to get inside the square root club, right? It's hopping in there. It's going on. So how does the a to the 4th get in the square root club? It's got to get squared, baby. So this is a to the 4th squared. What does that actually mean? Yeah, that's a to the 8, to the power of 8. Now, times a to the 1, how do I combine those? It's a to the 9, yeah. A to the 9. Okay? Right? A to the 4th is in there now. He's partying now in the square root club. Okay. This is a different club. This is the one down the street. Okay? From the square root club, this is the cubed root club. He's a little higher society right there. Okay? Some more rules there. They play classical music in that club. Not the dance stuff. Okay? All right? Now, if 5b wants to get into the cubed root club, what does 5b have to do you figure? Got to get cubed. All right, get cubed. So please don't forget to rewrite the index there. So 3b squared is already in there, and I got to get 5b has to get cubed. Okay? So now he's in there. He got cubed, so he's in the cubed root club. All right? So what is this? Well, 3b squared times. Now when you cube this term, you have to cube 5 and cube b. So what's 5 cubed? That's 5 times 5 times 5 is 125, good, times b cubed. Now we want to simplify, we can't leave it like that, so we got to go 3 times 125 is, I want to say 375, right? And then b squared times b cubed is b to the, do you add or multiply? Add. Okay? 375b to the 5th. Cube root 375b to the 5th. There's your answer. Okay? Now, I don't know if I'm a liar or not. Do those answers match with the answers in your textbook there for the examples? Okay, any questions about that? Because that's really important. If a number wants to get into the root club, it's got to get whatever it is, squared or get cubed or whatever. And then multiply by whatever's already in there. All right. Looks okay? All right. Here's your turn. Now let's go the other way. Let's go the other way, because this is the most important, really. This is the most important. So example 2 says express as mixed radicals. And this is simplifying radicals. Now, do you remember last chapter we talked a little bit about this? Okay. Again, I was assuming you guys knew how to do that. Some of you looked at me sideways a little bit. But anyways, so we always want to simplify radicals when possible. So let's go over that. Let's go over it officially so that we all know what we're doing here. Now, going from entire to mixed is called simplifying, and it's really the reverse process, guys, of what we just did. So think about this. 200, okay? This is a square root. So can 200 be split up into factors where one factor can be written as a square? All right, this is what you're trying to do. You're trying to find a factor of that number or that term in there that is a perfect square itself. So 200 can be written as what? We might even do a step before that. 2 times 100, or 2 times 10 squared. Does everyone see that? Okay. So again, what I'm doing is I'm trying to find a factor of 200 that is a perfect square. The perfect squares are, well, there's 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on, right? So these, you have to know these, okay? This is kind of baby stuff. You know this, I guess. But you should have these kind of in your mind. The squares, cubes, too. You should have cubes probably up to, 10 memorized, probably. Have those written down somewhere so you can refer to them. But anyway, so on. Squares and cubes. So watch this. Another rule when it comes to radicals is that you can actually split up the radical into its factors like this. So whatever is multiplied inside a radical can be split up into separate radicals that are themselves multiplied. So this is important to see, because what do I have here now? Look at this. The square root of 10 squared. The square root and the square totally cancels each other out. So the square root of 100 is 10. So now I have root 2 times 10. We always put the integer part at the beginning and the radical part at the end, and that is your solution there. Okay? Okay, so because this is so important, I'm going to give you another one, and I want you to do this. So, okay, tell me about this one. Simplify the square root of 32. Take one moment and do that. Here's your answer to square root of 32. In order to simplify this the quickest, you're going to want to choose the largest perfect square possible. Now, some of you may have done this. Oh, I know what a perfect square factor is. Root 4 times root 8. 2 root 8. And you might have said, hey, I'm done. Well, the problem is that we have to do another step of simplification here, because there's also a factor of 8 that's a perfect square. So if you did this, don't worry. You just have to kind of take a look again and say, hey, can I break that one up any further into a factor that is a perfect square? And the answer is yes. So this would be looking like this, right? Which that's 2 times 2 root 2, or 4 root 2. So you get the same answer, you just might take a little longer getting there. All right. Questions about that? Okay. There'll be lots of opportunity to practice. Let me do this one right here. Okay. When we're simplifying something that's a 4th root, or something that's larger than a square root, okay, and especially when we're working with variable terms, okay, it's a little trickier. Boys? Okay, c to the power of 9. Now, you have to think about this. What multiplies by itself 4 times to get c to the 9? Is there anything? No. Okay, so when we work with exponents, one of the easiest things to do is to think, hey, when I'm trying to get, if I'm trying to get c to some power, a 4th root, you have to think about, does this divide evenly by 4, right? And 9 does not divide evenly by 4, so that's not a perfect 4th root. But if we split it up like this, now we have an exponent that divides evenly by 4. So watch this. Okay? C to the 8 is actually c squared times c squared times c squared times c squared, isn't it? So c to the 8 is a perfect, has a perfect fourth root. So 2 plus 2 plus 2 plus 2. So 8 divided by 4 is c squared. So what times itself 4 times gives us c to the power of 8? The answer is c squared. This is your simplified version. So you might have to split that variable term up. Okay? And yeah, I'll just do this last one because this is important too, but I'll make some room here. Okay, so some more work with this. That one, if you didn't quite get that one, let's try this one and then maybe this will help. Okay? So square root, again, I want to simplify this or make it a mixed radical if possible, so I'm looking for factors of each part of this that are perfect squares. Perfect squares. So is there a factor of 48 that's a perfect square? So 4, 9, 16, 25, 16, right? So that's root 16 times what? Times root 3. Okay? So that's great. What about the y to the 5th? Okay, and you want to split y to the 5th up. Does 5 divide evenly by 2? No. But y to the 4th divides evenly by 2. So if I split this y to the 5th up like this, then boom, you see here's a perfect square and here's a perfect square. So you can simplify that and make those into integer numbers. So this is 4 times root 3 times, what's the square root of y to the 4th? It is y squared divided by 2. And this is root y. So now I multiply the non-radical parts. So I have 4y squared and multiply the radical parts. That is the square root of 3y. There is your final answer there. Okay? So a quick check would say this. Hey, if I squared this and put it in here, would I get my original answer back? And that would be 16y to the 4th. Well, if you simplified this, you'd get 48y to the 5th. That's the same as you started with, so this is your correct answer. All right, so example 3 asks you to compare and order radicals. Okay, so if you, we won't do this together, but just to see, if you wanted to say, to order these, what you might want to try and do is reduce them make them as simple as possible, or you might want to make them all entire radicals so you can just compare the numbers inside. Okay, that would probably be your best thing, and that's kind of what they did here. Look at the solution. Do you guys realize this? Here, I should point this out. If you have an exponent of 1/2, do you remember that that actually means square root? Okay, if you have an exponent of 1/2, that's the square root. If you have an exponent of 1/3, that means cubed root, and 1/4 is the 4th root, right? Okay, so that's really important as well. I'm not sure how much you're remembering here, like I say, but okay. So let's do part of this example as well. And this goes back to our combining like terms that we started off with. All right. Simplify radicals and combine like terms. So now we're putting two things together. So A, okay, A, root 50 plus 3 root 2. So in order to find out if these are actually like terms, what I should try and do, if I can, is simplify this or make this a mixed radical. Because this right now doesn't look like they're like terms. But if I change this root 50 into root 25 times root 2, I get 5 root 2. That's what root 50 actually is. So now, can I combine these? Are these like terms? The answer is yes. They both have a square root of 2 part. So they're like two apples. You can actually combine them into one term. So you have 5 of these, and you have 3 of these. That means you end up with 8 of these. Just add the number parts in the front. All right? B, I'll rewrite B here. And let's go over B because this is a good one. Root 80 is 2 root 12. Okay? So if we were to simplify these or try and combine like terms, I need to know if Any of these are like terms, because right now they don't look like it. But let's simplify to double check. So negative, if the negative is outside the root sign, that's totally fine. That doesn't cause a problem. It's only if it's a negative number inside the root sign is a problem. So is there a factor of 27 that's a perfect square? 9. Okay, this is actually root 9 times root 3. Okay, perfect. Can I simplify root 5? Is there a factor of 5 that's a perfect square? Now you might say 4. 4 plus 1, that's not a factor. Okay, so 4 is not a factor of 5. So this is simplified already. So we'll just leave that there. Root 80. Okay. Let's see. Perfect square factors of root 80. What can we split that up into? There's obviously 1, right? Like, I mean, 4 works. Does anything greater than 4 work? Like 16 or 9 or 16? Or does 80 divide evenly by 16? Okay, 16 times 5. You guys see that? And you can get your calculator out and just do 80 divided by 4. Oh, 80 divided by 9, 80 divided by 6. Whatever. If you need to, go ahead. So this is 16 times root 5. Good. Now 2 root 12. Okay. Can I split up root 12 into anything that includes a perfect square? 4, right. 4 times 3. So let's do that. Root 4 times root 3. Okay, everyone seeing what I'm doing here? I'm kind of like splitting these things up here. All right. Okay, we'll keep going. So this is actually negative. Root 9 is 3, root 3. This is, and then plus 3 root 5. This is minus 4 root 5. And this is minus 2 times 2. That's 4 root 3. Well, now we have some like terms. Awesome. This is a like term with this one. So negative 3 root 3 minus 4 is negative 7 root 3's. Those are dealt with. 3 root 5 minus 4 root 5 is negative 1 root 5. Or you don't have to put the 1 in front, right? So you can just go minus root 5. Okay, does that look good? Now I'll just make one note about C. Okay, one note about C. This letter C here. Don't worry about this. Okay, all this is saying is that it's saying, listen, don't worry, guys. This C cannot be negative. It's not going to like totally mess you up. It's all good. So don't worry about this. It's really just kind of saying, you know, we're not going to consider values of C that are negative here. That's all it's saying. So it doesn't factor into your calculations at all. All right. All right. So we're getting close to being done here this lesson. Anything else? Okay, there's some applications here. Pythagoras theorem, right? You might have to use radicals. See, look, radicals as values for triangles there. See? Okay. All right. Here's the key ideas. I'll let you take a look at that for a minute, and then I'll give you your assignment. Nope.
Can we get a paper back for what we wrote on first office?
Yep.
And we wrote formula research. Can we get?
Yeah, I think it's up there in the return pile. You can go grab it. Yeah, just walk around my desk here. You can go grab it. Yeah, I will. I will. You're welcome.